Hello students. We are going to start with the next problem in the backtracking. So in the last class, we have seen backtracking with the two examples. One is your Enkin problem and the other is your Hamiltonian circuit problem. So here I would like to move on to the next problem, that is your sum of subset problem. So before going into sum of subset problem, I would like to tell what we have seen yesterday for the backtracking. What is this backtracking technique all about? So we have seen yesterday that backtracking is nothing but it is a method or a technique which is used for getting the exact solutions, where it is mostly used in the combinatorial problems, which is classified as the NP-hard problems. And here the backtracking will be eliminating some cases which is unwanted. And when you go ahead with the backtracking, we are going to see it by constructing a state space tree. So yesterday we have seen that for a state space tree, we will be having a set of nodes as well as edges. The nodes are considered to be the partial solution. And what is this edges all about? There are various choices. You can opt for any choice. Okay, we will be going one after the other. We will be seeing all the choices which will extend for getting our partial solution. Now, as I told you yesterday, for backtracking, we have two different graph traversals. The two traversals are nothing but the depth first search and the breadth first search. So in backtracking, what we do is we go ahead with the generation of the state space tree is done with the help of the DFS. That is your depth first search. So you have two types of nodes, promising and non-promising nodes. Non-promising nodes will not lead to a solution. So those nodes are called as the dead ends. When you come across with a dead end or a non-promising node, you will be saying that you need to move to its parent node, backtrack it. Backtracking is nothing but moving to its parent node and continue the search from there onwards. If it is a promising node, it may further lead to a solution. So we will be going forward. So the name backtracking is obtained by saying that if you get a non-promising node or a dead end, we will be tracking back, or we will be moving to its parent node. Clear? So we will move on to the next problem. In the last class, we have seen the NQ problem. We have seen the Hamiltonian circuit problem. Now we will go on to the third problem, which is nothing but it is called as the sum of subset problem. So what do you mean by this sum of subset problem? This problem can be traced out manually. Okay. So when you go with the sum of subset problem, you will be given with a set. As I have mentioned earlier, that it is a combinatorial problem. So we can create various combinations. Combinations are nothing but the subsets. But always keep in mind that when you are creating the subset, the sum of all the values which is chosen in the subset should give you a positive integer, where the positive integer is also been mentioned over here in this problem. So you will be given with a set of positive integers. It can have n positive integers, and also you will be given with a m value. You can see here in this example, you can see here, you are given with a set which consists of 5 elements, and also you are given with a m value. So if you create a subset, the subset should consist of, if you have the subset, if you find out the sum of all the subsets, all the values in the subset, it should get a value, give you a value as m. It should be exactly equal to m. It cannot be neither less nor it can be greater. So, for example, what is given here? The set S, which is having 5 elements, 1, 2, 5, 6, 8. And you have the m value which is equal to 9. So now from this you will be getting two solutions. What are the two solutions? The two solutions are nothing but you are saying that you can create a subset which consists of the elements 1, 2 and 6, and another subset which will be consisting of 1 and 8. So here it is very convenient to first sort the elements in the increasing order. So whatever the elements are given, it need not be given, the input need not be a increasing order. What we do to solve it, before solving, to get an appropriate solution, we need to sort the elements in the ascending order. So here it's given S1 less than or equal to S2 less than or equal to S3, etc. up to Sn. So which indicates that the elements in the set is being sorted with the increasing order. Now, once when you go for a problem using the backtracking technique, there will be certain constraints for the problem also. We need to satisfy the constraints. What is a constraint right now here? We are saying that the value of the sum of all the values in the subset should be exactly equal to m. So here, even if it is less or greater, it is going to be ignored. So here we are going to, each time when you generate it, we are going to record the value. The value is mentioned as S dash, where it will be S dash is nothing but whatever the value is selected in the list so far. So for example, when you go to the step as 1, 2, what is 1 plus 2? 1 plus 2 is equal to 3. Whether 3 is equal to 9? No. So we may go to the next one. What is the next value? The next value is 5. So 1 plus 2 plus 5 is 8. Next, when you go for next, choosing next element, 8 plus 6, it's equal to 14. 14 is greater than 9. So you are not supposed to take it. Okay. So this is how we just select the values. So when you find that it is a non-promising node, you are backtracking. When it will be a non-promising node, if the sum S dash is too large or the sum S dash is too small, we say that it is, the inequalities are not satisfied here. So we will be saying that it is a non-promising node. Once when you encounter a non-promising node, we are backtracking to its parent node and going for the next choice. So this is how we solve the sum of subset problem. So initially you are given with the root node. Okay. What is the root node value? The root node value, we will assign it as 0. Now compared to your previous problems, in your previous problem, if you see any node, if you take, it can have either 2 children or it can have 3 children or it will be having only 1 child. So the number of children are indicating the number of choices. For example, from A, you can have 3 choices. You can, next path can be either from A to B, A to C or A to D. So there are 3 children. Now, if you take D, D is having only 2 options, C and E. So there will be only 2 children. So it is the number of choices is based on, the number of children will be based on the number of choices. So here in a sum of subset problem, it's not going to be a dynamic one. It's going to be a static. It will not be varying each level. It is not going to vary. Each level, if you see, each node can have only 2 children. Because here in sum of subset problem, we are either including the element or we are excluding the element. So here, when you say it as the left child will be including the element, Right child says that it is going to exclude the element. So we are given with a set which consists of 4 values, 3, 5, 6, 7. And we will be given with a m value which is 15. So here we need to find out the subset which is equal to 15. So first we will be arranging the elements in the ascending order. So we have already arranged the elements in the ascending order. Now we start with the tree structure. So when you initially start with, the value is 0. So now we will be going for with 3, with the element 3. When you say it as with element 3, what happens? The S dash value, what is that in your node, that will be changed. The reflection will be based on whether you are including the item or excluding the item. If you are including the first item, 3. So what is 0 plus 3? 0 plus 3 is 3. Got it? So here initially we will start with root node with 0. If you include an element, then that element will be added with the root node value and you will be getting a new S dash value. S dash value is the sum of 0 plus 3, which is equal to 3. Next again, it is a depth first search, so you need to complete this entire path. So next, what is the next element? The next element is 5. So we are saying that with 5. What is with 5? The with 5 is, it is 5 plus 3 is 8. Now again you have 8. We are going to include the next element. The next element is 6. So with the 6, if you see, it is 14. So now our value is 15. You are supposed to get it as 15. So here what we do, 14 plus 7, what is the value? It is greater than 15. So it is a non-promising node. 14 plus, if you are not including this item, what it will be the value? 14 plus 0, it will be less than 15. It cannot be neither less nor greater. So this becomes a non-promising node. We are backtracking, moving to its parent node. So the left child is already worked out with including with an item. So we are moving to the next one without the item. When you say it as without item, what is 8 plus 0? It is the same. It is 8. Now, what is the next item? It is now we are in the 4th level. So the next item is 7. So you are going with 7. 8 plus 7 is 15. So here we got the solution. Now, without 7, if you see, what is 8? Without 7, 8 plus 0, it is 8. 8 is less than 50, so it is a non-promising. So we backtrack, go to its parent node. We have only 2 children at any level. Both the children are worked out. So we are again moving back to its parent node. Again, 2 children are worked out. So we are again moving to its parent node. So now we are at this level where only the left child was worked out. Left subtree is completed. So we move to the right child. When you say it as right child, this is your second level. So now again you are saying that already with 5 is included. It's been done. So now without 5, excluding the second item. Excluding the second item means 3 plus 0, it is 3. Clear? So 0 plus 3 is 3. Now with the next item means with the 6. 6 is 3 plus 6 is 9. What is the next one? Next one is 7. So 9 plus 7, it is greater than 15. 9 without 7, it is less than 15. So we are not able to solve it. So it's a dead end. Non-promising node. Non-promising node means backtracker. So without 6. So without 6, the value is 3. So including the next item 7 also, it is less than 10. 3 plus 7, it is 10. So 10 is less than 15. So it is a non-promising node. So we backtrack. We again backtrack. Again we backtrack. So the entire left subtree is over by including subsequently all the items, or excluding the items we have worked out. Now we will be moving on without 3. Without 3 means you are not including item 3. When you are not including the item 3, what will be the value? The value will be 0. So now we check with 5. What is with 5? 0 plus 5 is 5. So we will move on to the next level where it says that we are going to include the next element. So 5 plus 6 is 11. But when you go for the next level, the value becomes 11 plus 7, which is 18, which is greater than 15. So it is a non-promising node. Next, we will be moving on to its parent node. 5 without 6. 5 without 6 is just 5 itself. But what is the item which is left out? Only we are left out with 7. Even if you include 5 plus 7 also, it is only 12, which is less than 15. So can we include it? No, it is not possible. So we are just saying that this is a non-promising node or a dead end. When this is a non-promising node, it is backtracking. Here we are supposed to complete 2 children. Both the children are over. It is been worked out. So what we do is we next move on to its parent node. So here if you see, the left child is by including item 5. So what will be the right child? Right child says that we are excluding that particular item. Clear? So when you say it as without 5, the value will be still it becomes 0. So in the previous case, we have seen the constraints by saying that there are 2 inequalities. The 2 inequalities are nothing but if you have updated the node value as s dash, and whatever remaining element, if it is left out, whatever left out remaining elements, even if you add all the elements, if the value is less than some, the s dash is too small, and you are saying that the inequality doesn't hold good for getting the solution, and it becomes a non-promising node. So here you can see here, suppose if your s dash value is after including 2 items, we are saying that after including 2 items, you have a value. Now, if you include all the remaining values also, even if you are not getting, if it is less than, if it is less than 15, then we say that the sum is too small and we cannot go ahead with it. So, what are the remaining elements you have? You have the remaining elements as 6 and 7. So 6 and 7, the value is 13. But what is the value which is updated here as s dash? It is just 0. So 0 plus 13 is 13, which is less than 15. Have you got it? So this is how we will be going for the sum of subset problem. Now the entire tree structure is over by completing the inclusion of and exclusion of all the items in the given set. So now we need to find out whether you have obtained a solution. If you have got a solution, just from the root node till you reach that particular leaf node, find out what are the edges you have. What is the choices you have been taken to get the solution. What are the choices? With 3, it says that next level, it says that with 5. Third level, it says without 6. And the last level, it says that with 7. So 3 plus 5 plus 7. So 3 plus 5 plus 7, we are getting the solution as 15. So your subset will be having, there will be only, because there is only one solution. It is not like the previous 2 cases. In the previous 2 cases, if you are asked for a single solution, we can stop it. But here, you need to generate all the subsets. So we need to trace the entire tree structure to find out what are the subsets. So in this case, we have obtained only, we have come up with only one subset, which says that the elements are 3, 5 and 7. So 3 plus 5, 8. 8 plus 5, 8 plus 7, it is 15. So 15 is your solution. Is it clear? So this is all about the sum of subset problem. Sum of subset problem is nothing but you will be given with the integers, and you will also be given with a positive integer. So we need to find out whatever the integers, we have to first initially we need to sort the elements in the increasing order. Then when you are given with the value, you need to find out whatever the integers given in the subset. When you add it up, will you get this integer? If you are getting the integer, then we will be getting it as that subset will form a solution. So it can be either a single solution or you will be having multiple solutions. So whenever you go for such types of problems, keep it in mind that because it is a subset which is forming. Okay. In Hamiltonian circuit, if you see, if you want to find out a solution, the solution will be consisting of all the vertices. In the n-cune problem, you would have seen by placing all the n-cunes in its proper position, we are getting a solution. But whereas in the sum of subset problem, it is not like that. We are just creating a subset. The subset need not have all the elements in the given input. It will be having only few integers. So here we construct a tree which is of static form. Always in any level, if you take in our first level or second level or third level or fourth level, if you take all the nodes will have only two children, the left child and the right child. It is a binary tree. Binary tree will be consisting of only two children at any level. So similarly, here also we have only two children, which says that the left child will always be with including the item. The right child says that it is excluding the item. And each time when you take the node value, parent node value, the node value has to be updated by considering whether it is a left or the right. If it is a left child, add the value with the root node or with the previous node. But if it is a right child, the same value is being retained. Why? Because it is not including the item. So at any point of time, when you say that the value is either greater or when it is less than, you are saying that you will not be able to get a solution. The solution will be obtained only when you get the exact value of m, you will be getting a solution. So it can be either a single solution or it can be a multiple solution. So now, there are certain cases where we may not be able to get the solution also. For example, here you are given with a set of integers is equal to 3, 5, 7, 9 and your m value is 12. Are you getting a solution? Yes. If you say 5 plus 7, it is 12. If you say 3 plus 9, it is 12. So you are getting the solution. But whereas in the first case, if you see this first case, you have a set as 1, 6, 9, 12 and the m value is 40. Even if you add all these values, if you have a subset which consists of all these positive integers, what is 1 plus 6? It is 7. 7 plus 9, 16. 16 plus 12, 18 plus 28 it is. Okay, so 1 plus 6 plus 9 plus 12 is 28, which is very, very less than 40. Getting it? You are saying that you are adding all the numbers. See what is the value. If the sum of all the integers is less than m, then you will not get a solution. Similarly, we will come up with the second one. What is the second one? It says, the second one says that you have a value as 7, 12, 13. And what is your m value? M value is 6. So here, if at all, if you have a value as is equal to 7, 12, 13. What is your m value? M value is 6. So the first value which is given, for example, if you consider S1, S1 itself is greater than m. So will you get a solution? No, you will not get a solution. So here the sum of all the values, if you take the sum of all the value is, that is, if you say 1 plus 6 plus 9 plus 12, it is equal to 28. 28 is less than 40. 28 is less than 40. Sum of all the integers are less than 40. Now here the first S1 value itself is greater than M. So will you be getting a solution? No. So these two cases, if you see, you will not get a solution. Understood? So you are not going to get a solution for the value which says that it is, you will not get a solution when the total of all the values is greater than less than M, and if the first integer itself it's greater than your M value, you will not get a solution. Whereas here in this case your M value is 15 and you are saying that you are getting a solution. Okay, so that's all about the sum of subset problem. So we have an algorithm here by taking the first two, these two, if you consider with based on that, we are saying that we assume when you write an algorithm, we are assuming that your W of 1 should be less than M. And if your sum of all the values, if you see, it should be greater than or equal to M. Okay, W of 1 should be, that is your first value itself, it should be less than or equal to M. Only then you will get a solution. Or the sum of all the weights of all the values, if whatever you are taking, it should be greater than or equal to M. Here we have seen when it is less than M, we have not got a solution. So it should be, obviously it should be greater than or equal to M. So we know that we are going to generate the left child. Left child will be saying that you are going to include the item. So when you say it does include the item, what will be the value? The value will be 1. But when you are going to exclude the item, the excluding the item says that it is 0. When it will be excluded for the right child. So first we will complete the generation of left child. We are saying that x of k is equal to 1, and we will be saying that S plus W of k, whether it is equal to M. Then you will be getting a subset and you are writing all the integers. Otherwise, you need to add the next value. With the current value, you are not getting the value. So go for the next element. If it is less than or equal to M, then call this algorithm recursively by passing 3 integers. What are the 3 integers? The 3 integers S, K and R. What is S now? It is updated to S plus the current value W of K. You are going to include the next items K plus 1. We will be seeing what is left out when you go for including the next item, what is it left out. Whereas when you generate the right child, you are saying that you are checking whether S plus W, R minus W of K is greater than or equal to M, and whether S plus W of K plus 1 is less than or equal to M. Then you are excluding the item. If it is greater or less, we need to exclude. So your X of K will be 0. So you are calling the sum of subset. See here we are including the item. So we are saying it as S plus W of K, current item. But here we are excluding the current item. So it is only S. The second parameter is common in both the thing. In left also you are saying K plus 1. Right also you are going to move forward for the next item, that is K plus 1. For in both we need to also check what is the remaining capacity. R minus W of K. Here also we will see what is the remaining value, that is R minus W of K. Clear? So now generally when you say it as backtracking, we will be using various tuples. So there will be n tuples to generate the tree, and this algorithm which says that you are going to find out a solution and obtain it if it is satisfy the constraints. For each and every element which is belonging to the subset, we have to see whether the constraint is satisfied. If the constraint is satisfied, we are including it. Otherwise, we are backtracking, calling the same recursive algorithm for the next item. So to conclude for this backtracking, what we are doing is, first we are taking, it's applied only to the combinatorial problems for which there is no known algorithms, or you can say that we don't have an efficient algorithm for finding the exact solutions. Okay. Now, in SOST search, in the second module in under brute force, we have seen the SOST search approach. What it says, it generates all the various subsets and then it finds a solution which is very, very slow. If it is a very small instance, probably it may work it out. But for very large instance, generating all the solutions and finding a optimal solution, it's not that feasible. Okay, but here in backtracking, whenever we don't want, we feel that it doesn't give a solution, it leads to a it doesn't lead to a partial solution, we backtrack it, we ignore, we will not consider all the cases. Whenever the case says, choices says that it doesn't lead, we will be backtracking it. So in backtracking, it will not eliminate any elements of the problem state space and ends up generating all the elements, provides a technique where you will be having its own value for its own writer. Okay, so this is all about your backtracking. So in a backtracking, we have seen that there are two things. One is your nodes and another is your edges. Nodes will be giving you a partial solution. Edges are the choices which leads to the partial solution. You are going to generate the state space by using the concept of depth first search. And next, third thing, it says that whenever you go for the node can be a prune node or a non-promising node. If it is a non-promising node, we just backtrack it. We will not go further for taking the solution. So for a backtracking, we have seen with the three problems. One is your NQN problem, the next is your Hamiltonian circuit, and the third is your sum of subset problem. Except sum of subset, the other two is dynamic. Based on the number of choices it has, the number of children varies. But whereas in the sum of subset, you please keep in mind that it is a static tree. Always it will have only two children. The two children, when it comes into picture, that is when you are going to select some of the elements. In a NQN, all the QN has to be placed. In a Hamiltonian circuit, all the vertices should be considered. But whereas in sum of subset, we will not be considering all the items. We just get a subset. For example, here there are 4 elements. To get the solution, we have not considered all the 4. We have taken only two of them. Any two. First case it was 5 and 7. The second case it was 3 and 9. It can be anything. It can be 3 also. It can even be 4 also. Okay, but it is based on what is your value. So it will be always consisting of only 2 children at any point of or any particular levels. So the 2 children are nothing but the left child and the right child. The left child will be including the item. The right child will be excluding the item. Hope you all are very clear with this backtracking technique. The backtracking technique we will be using for all the combinatorial problems, which belongs to the NP hard problems. We have already seen what is this NP hard problems. So it is all about how to deal with the NP hard problems. Okay. At the end of this chapter, I'll be giving you some exercises which you can work out even for the set. If you take this set S equal to 3, 5, 7 and M equal to 12, you can you can just find out whether you will be getting a solution by drawing the tree structure, not manually, by drawing the state space tree, find out the solution for this particular set. The set is 3, 5, 7, 9 and m equal to 10. So try to identify the subsolutions by generating the entire state space tree, which will be consisting of 2 children always. And the two constraints you need to keep it in mind, that is s dash plus si plus 1. If it is greater than m, you consider s dash is too large and it becomes a non-promising node. If s dash plus summation of j equal to j plus 1 to n, sj is less than m, it is s dash is too small, so it also becomes a non-promising. So greater than m or less than m, it is considered to be a non-promising node. If you get the exact solution, then it becomes the solution, and you find out what are the subsets. You can find out by seeing the entire path from the root node till that particular leaf node. You find out what are the edges you have. Based on the choices of the edges, you will be saying what all elements are included. Here in this case, 3, 5, 7 are included because we are saying here as without 6. Hope you are clear with the 3 problems. Okay, please try out all these problems, and if you have any doubts at any point of time, when you try it out, you will come to know what is the difficulty you have in tracing it out. If you have any difficulties, you can just clarify with me. Yeah, okay. Next is branch and bound. So the branch and bound technique, we will see it in the next class. So here in backtracking, we have seen the NQN problem, Hamiltonian circuit problem, and the sum of subset problem. In the next class tomorrow, we will deal with the branch and bound technique. Hope you are clear with this topic. Any doubts, any clarification, please get back to me. We will, I will just revise it. Thank you all.